Okay, welcome back to the Chapter 5 exam review. This is part 2, so this will cover the second half of the practice exam. So if you want to see the first half of the test, you'll need to go find the video for part 1 of the exam review. We're going to pick up here with section 5.5, which is on solving equations involving rational expressions. And so our first equation is going to be this one here. And whenever you have an equation where it's just one fraction on the left-hand side and just one fraction on the right-hand side, there is a shortcut we can use to solve this kind of equation. It's called cross-multiplying. So that's what I'm going to do here. I'm going to cross-multiply. And the way it works is you multiply the opposite corners together, if you will. So I'm going to take this x plus 2 and multiply it to the 4. So I'll have x plus, I'll do it down here. I'll have x plus 2. I'm going to put it in parentheses because it has to get multiplied by 4. The whole thing does. And then I'm going to take, I'll do a different color for this. I'm going to take x times 5. All right, so I'll have x times 5 here. And the most important thing if you're using the shortcut, because you would be surprised at all the different things I've seen students do with these results, you need to set these equal to each other. So whatever you get from your results from cross-multiplying should still be equal to one another. So put an equal sign between those two results. Don't add them together, don't divide them, or anything else. You want to set them equal to each other. And so we're going to simplify here by distributing the 4 into the parentheses. Right, and so I'm going to have 4 times x, which will be 4x, 4 times 2, which is going to be 8. And then x times 5, I probably should have just done this from the beginning. We're just going to write that as 5x. And then you solve from here, right? So we're just going to get x by itself on one side. I'll do that by, and this one works out really nice and easy. Subtract 4x to the other side, and you get x is equal to 8. All right, and so we will select option A, and in the box we'll type in the number 8. Notice there are some other options. I will address those as they come up, but for this problem, that's all there is to it. So not too bad, not a bad way to start out. Now this is kind of a bad way to follow up. So we have this crazy looking equation. We have y over y minus 15 plus y over y squared minus 225 equals y plus 16 over y plus 15. So this one, you can't use the shortcut we just used on the last problem because there's more than just one fraction on the left-hand side. We have 2 fractions over here. So the shortcut is out the window. We're going to have to use the general process, which is very similar to simplifying the complex fractions that we saw in the last video. You will factor your denominators, find the LCM, the common denominator, and then multiply it to both sides of the equation to get rid of all the fractions. So first we'll start by factoring. So this y squared minus 225, that's the only thing we can factor, but I'm going to copy everything else down. So we'll have y over y minus 15 plus y over the y squared minus 225. Again, is the a squared minus b squared formula that we saw so many times on the last video. This one, the number's a little bit big, but look at the other factors to kind of give you a hint, right? This one's y minus 15, this one's y plus 15. They're likely going to share some in common, so 15 is the number you want to use there. Factors is y plus 15, y minus 15, equals y plus 16 over y plus 15. All right, so we have it factored. Now we can find the LCM, the common denominator. Right? The LCM, we take every factor that occurs, so I look at all my denominators. The factors that I see occurring are y plus 15 and y minus 15, and that's it. I don't see any other factors here except for those 2. Raise each one to the highest power. It's all to the first power. So we're good to go. We're going to multiply the LCM to both sides of the equation. So we're going to multiply y plus 15, y minus 15. And a lazy way of multiplying it to both sides is just to put parentheses around the whole equation. So I'm multiplying this throughout the whole equation. So we're going to distribute, and it gets multiplied to both sides. Right, and all the fractions essentially. So it's going to get multiplied to this, it's going to get multiplied to this, and it's going to get multiplied to this on the right-hand side. And just like we did with the complex fractions on the last video, I don't want to have to write it out explicitly in detail for each individual fraction, so we're just going to try to work it out mentally, what's going to cancel out, what's going to be left over. So think of this as being over 1. When this gets multiplied to the first fraction over here, what's going to cancel out? is the y minus 15s. Those are going to cancel each other out. So what's going to be left over is the y I have here to begin with times the y plus 15. That's what's left over from the LCM. Now I'm going to remove the markings I made here because a fresh copy of this has to get multiplied to the next two fractions. So I don't want to have this marked up. So I'm going to undo that last mark. So just keep that in mind mentally. The y minus 15 is getting canceled out in this situation. So I'll have the y that was here to begin with times the y plus 15. And again, the y minus 15 went away. Okay, then we have plus a fresh copy of this gets multiplied to the second fraction. And what's going to happen here is both the y plus 15 and the y minus 15 is going to cancel out. So both of those are going to cancel out, and all I'm going to have left over from this is the y that was here to begin with, because both of these factors are going to go away with these two factors here. And so again, I'm going to undo those markings. All right. And so remember, mentally, we're going to keep track of this. Both of these factors cancel out. All we're going to have left over is the y. Equals, on the right-hand side, again, a fresh copy of this gets multiplied to this fraction. The y plus 15s are going to cancel out. So what I'm going to have left over is the y plus 16 that was here to begin with times the y minus 15 that's left over from the LCM. Okay, so I think this is the first time I'm encountering this issue. I'm a little worried about having the space necessary to finish this problem on the screen because it's not going to be easy to adjust. I can't really scroll down very easily. So with this program, anyways, it doesn't look like it. So we'll see what we have to do here. Hopefully, I don't butcher it too bad. So now we need to solve this equation. We got the fractions out of the way, which is great. So now I need to solve this equation that I have, and I'll start by distributing the y into this parentheses. So we're going to get y squared plus 15y. This plus y just gets copied down, equals, on the right-hand side, we'll have to FOIL. First, outer, inner, last. So we'll get y times y, which is y squared. Y times negative 15 is negative 15y. 16 times y is positive 16y. And this is going to be a big number. 16 times negative 15 will be negative, I think it's going to be 240. And I only know that because 15 times 15 is 225, and we want another 15 on top of that. So that'd be 240. Okay, so then we'll combine like terms. So this will become y squared plus 16y when we add these two together, equals, this will become y squared plus 1y minus 240. All right. So it looks like initially we have a quadratic equation, but what's going to happen is these y squareds are going to cancel out, and if the y squareds cancel out, it's not quadratic anymore. All right, I'm going to pause it here for a second and see if I can make some more space for me to continue working this problem. So just be 1 second. Okay, so I figured out I can scroll up and down. So next time that has to happen, I shouldn't have to pause the video to do that. So here's a little bit more space for us to continue working. So what's going to happen here is we're going to subtract the y squareds to get them on the same side. But what's going to happen is the y squareds are just both going to cancel out. So those cancel out, those cancel out. And we end up with 16y equals y minus 240. So it's not even a quadratic equation anymore. It's now a linear equation. And so the way we solve a linear equation is we get x, or in this case y, by itself on one side. And so we'll subtract the y over to this side, so we get 15y equals negative 240, and then we divide by 15 on both sides. And we end up with, I'll just write it over here, y equaling negative 16. And so that would be my final answer. And so going back up to the top, let's see if I can use this scroll button like I was doing before. So going back up to the top, you would type that into this box here. So again, it's kind of a normal problem. You get negative 16, you type it into that box, and you're done. All right. Okay, so let's move on. Let me just kind of scroll back down here so you can get the last of that. And we're going to move on to the next kind of equation. Now, hopefully this next one's going to interact with some of the other options we have for these problems. So let's take a look at what we have here. All right, so very similar kind of problem, similar kind of setup. We're going to approach it in a very similar way. we are going to factor first. So that means factoring this denominator here. So I'm going to write the problem down again. We have 4z plus 2 over z minus 3 equals 84 over z plus 3, z minus 3, plus 4z minus 2 over z plus 3. Right, so we get it factored. Then we find the LCM, just like we did last time. Right? Take every factor that occurs. So the factors I'm seeing here are z plus 3 and z minus 3. Raise each one to the highest power that occurs. They're all to the first power. And so that's going to be my common denominator. I multiply it to both sides of the equation. So this is the way I like to annotate that. So just putting parentheses around the entire equation. Think of this as being over 1. And we will distribute. I'm sorry, there's just no clean way for me to do this. So we multiply it once to each fraction. And what's going to happen here is that a fresh copy of this gets multiplied to the first fraction. What's going to cancel out are the z minus 3's. But again, we're doing this mentally. And what's going to be left over is 4z plus 2 times z plus 3, right? Those two factors are going to be left over. And so that's what I'm going to write down here. But I'm going to undo the crossing out because a fresh copy of this has to get multiplied to these other fractions. So again, mentally keep in mind what's left over here is the 4z plus 2 times the z plus 3, because the z minus 3 is the one that got canceled out. All right, so that's my result on the left-hand side. On the right-hand side, I feel like we're going to get a very similar result this time too, which I want to get something different here. I want to get a quadratic equation, and I don't think that's going to happen here either because these are just too similar to each other. So a fresh copy of this gets multiplied to the next fraction, and both the z plus 3 and the z minus 3's are going to cancel out. And so all I'm going to have left over here is the 84. However, I'm not going to leave this marked out because a fresh copy has to get multiplied to the next fraction, so let's undo that. Just keep in mind that both of these got canceled out with these two down here, so all I have left over is the 84. Plus, for the last case, the z plus 3's get canceled out, so what I'm going to have left over here is 4z minus 2 times z minus 3. All right. Okay, so this is the resulting equation we get. We need to multiply it out, so I will FOIL over here. I'm not going to draw all the arrows because I don't do a very good job of it anyways. So we get 4z times z, which is 4z squared, 4z times 3, which is 12z, 2 times z, which is 2z, and 2 times 3, which is 6. On this side, we're going to have 84 plus, same kind of thing happens over here. We get 4z squared minus 12z minus 2z plus 6. All right, and so we combine like terms, just like we did last time. So we're going to get 4z squared plus 14z plus 6 equals, here the 84 and the 6 can combine together. So let's go ahead and put this first. 4z squared minus 14z, but don't forget about the 84. 84 plus 6 is going to give me 90, right? And then we're going to need a little more space. So now that I know how to do that, let's go ahead and get a little bit more space here. It's a lot easier than I thought it would be. So now, again, it looks quadratic. I wish it stayed quadratic, but what's going to happen, because I want to do an example of that, but I guess it's just not in the cards. The z squares are going to cancel out. And if they cancel out, it's not quadratic anymore. Right? So we subtract the 4z squared to the other side. They both cancel out. And so it's going to be linear. So we end up getting 14z plus 6 equals negative 14z plus 90. So to solve a linear equation, you get your variable to one side, everything else to the other side. So I'm going to add 14z over to here. And while I'm at it, I'll just go ahead and subtract the 6 over here. Right, no reason to wait on that. Right? And then we're going to end up with 28z. So if you thought the z's were going to cancel out, it doesn't quite happen. The signs actually work out where it stays in the equation. Okay, that cancels out, and we get equals 84. All right, so I'm hoping for a certain kind of result here. Let's see if we get it. Divide by 28 on both sides. and we're going to get z is equal to 3. Right? And that's actually kind of what I wanted to see. So get z is equal to 3. All right. And you go to type that into Math Excel. So you're like, okay, great, I have an answer. So just like the last two problems, you go up here and you think, I'll just type in z equals 3 here. But here is the issue that I was hoping to address at some point. 3 can't work in the original equation. So if you go back to the very beginning, the original equation that we started with, this equation here, or this one is even better really, but I have more room to work up here. Whenever you have a fraction that has a variable in the denominator, something you have to be careful about is dividing by 0. We don't want to plug any numbers in for z that would make me divide by 0, because then that's a broken equation. It doesn't work if you're dividing by 0. It doesn't produce results. So I have to avoid using those kind of numbers in this equation. So if I go back to here and I look at this denominator here, what number would make this denominator equal 0? Because that's a number I need to avoid. And it turns out the number that would make this equal 0 is 3, right? If z is equal to 3, and you plug that into this denominator, you get 3 minus 3, which is going to be 0. And it doesn't matter what you get in the numerator, you're dividing by 0. It doesn't produce a result, so it doesn't actually solve the equation. Also, in addition to that, we also have negative 3 that's a concern for us. So under no circumstances can z equal 3 or negative 3, because then we're dividing by 0. This denominator has the same two restrictions, right? Once you factor it, you see it's the same two numbers that would cause 0 here, negative 3 and positive 3. And so under no circumstances can I accept these numbers as solutions. It just doesn't work in this particular equation. Well, guess what we ended up getting down here, right? We got z equals 3. Well, that's no good, right? That's not actually a valid solution to this equation. So why did we get that? Well, when we multiply this LCM to both sides, we actually, it's a mathematically acceptable operation, but the result we get here isn't really the same as the equation we started with. This equation has limitations. You can't have negative 3 or positive 3 in this equation. This equation right here doesn't have any limitations. There's no restrictions here. So 3 is a solution to this equation that we have here. But that's not the equation we were trying to solve. We're trying to solve this one right here, and 3 doesn't work in this equation. And so that's why we ended up getting that as a solution, even though it doesn't work in our original problem. So long story short, 3 is not a valid solution, so we have to toss it out. That's no good. And since there's no other alternatives, there's nothing else that could possibly work, our conclusion here is that this equation has no solution. If that's the only possible answer and it's not a valid answer, then there's just no solution to that equation. So the final answer we're going to select here in Math Excel is going to be this one here, option C. There's no solution to this equation. All right. So be on the lookout for that. If you go back to our previous examples, it's another concern we should have had, but it just didn't come up, so I didn't mention it. But here in this equation, we can't accept 15, right? 15 doesn't work in this equation. Under no circumstances can we use that as a solution. And for this one, negative 15, right? So we had similar restrictions in this equation, but the solution we got was negative 16, which is fine, right? It doesn't make me divide by 0. It's a perfectly valid solution, so we keep it, right? All right. So I think that's it for the equations. All right, sorry, my program might have froze on me. This is not good. Okay, here we go. All right. All right, now we're on to the word problems. Okay. John can cut and split a cord of firewood in 6 fewer hours than Steve can. When they work together, it takes them 4 hours. How long would it take each of them to do the job alone? Now, I think if you look on Math Excel, it has a formula that you can use to do this problem, but I prefer to do it in a little bit of a different way. So what I do, it's kind of like what we did before when we had word problems in Chapter 3, is I set up a table, right, to organize this information. This is a work problem, and I don't know if we had work problems before, but for a work problem, the formula that applies is W equals RT. And it's very similar to D equals RT. It's the distance formula, except it's for work instead of the distance you travel, but it's the same concept. R is how fast you work, So how fast the work is done is probably a better way for me to say that. How fast the work is done. Right. T is the time. How long are you working for? And then W is the amount of work that is done. All right, so that's how that formula works. And this formula applies to both John and Steve. So that's why we need a table, because we have one formula that applies to two different people. So we'll make a table, we'll make a row for each thing the formula applies to. So it applies to John, it applies to Steve. So we'll label it that way. And we'll make a column for each variable in the formula. So we have R, we have T, we have W. All right. And so we need to fill in this table. Now what we need to keep in mind is that this table is for the situation where they're working together. So that's the information I want to put here is, what do I know about the situation where they're working together? So when I go back and read through the problem, the first number I come across is John can split a cord of firewood in 6 fewer hours than Steve. So it tells me something about, it seems like it's about a time, but in fact, this is actually telling me their speed, how fast they work. So by knowing this, I can tell you who's the faster worker, right? Who works faster? It's John, because he gets the job done in 6 fewer hours than Steve. So Steve is slower, John is faster. That has to do with their speed, how fast they work. So don't put the 6 fewer hours in for the time. It's actually given to us so that we can understand their speed. Now, I don't know how fast Steve gets the job done or how fast John gets the job done, because what they give me a clue, but I don't know specifically. Like, is it 10 hours for Steve? Is it 12 hours for Steve? I don't know. So I'm going to call that X. I'm going to say Steve gets the job done in X hours when he's working by himself. If that's true, then for John, when he's working by himself, it'll take him X minus 6 hours, right? 6 fewer hours than Steve. And what we're going to do with this is we're going to make a speed out of this. And so to show you how you get the speed, we have to kind of take a break from this table and consider the case where, let's say, Steve is working alone. So if Steve is working alone, we don't need a table for that situation because he's by himself. We just need this formula. And when he's working alone, the time it takes him is X hours, right? That's what we're putting here. It's going to take him X hours to do the job alone. I don't know his speed. That's what I'm trying to find out. And how much work is he going to get done in that amount of time? We have to put a number here for that. And so this is kind of another tricky thing about work problems, but we keep it as simple as possible. We just say he gets one job done. We're not going to say we could say he splits a cord of firewood, right? It's 1 cord of firewood. But we're not going to say it's like 100 logs or whatever, right? We're not going to like try to get that specific. It's just one job gets done in whatever amount of time it takes Steve to do the job by himself. And then we solve that for R by dividing X on both sides, right? And so we get that Steve's speed is 1 over X. It's 1 over however much time it would take him to do the job alone. That's going to be how fast Steve works. And so that's what I'm going to put here for Steve's speed. So hopefully you see the pattern there. It takes Steve X hours to do the job alone, so his speed is 1 over X. So what are we going to put for John? It takes him X minus 6 hours to do the job alone, so his speed is 1 over X minus 6. All right, now you can see why this is in Chapter 5, because this is the kind of stuff we're doing in Chapter 5, right? These rational expressions. Now for the time, when they're working together, it takes them 4 hours. So they're starting at the same time, they're ending at the same time. So they're working the same amount of time. John is going to put in 4 hours when they're working together, and so is Steve. He's going to be working right alongside him for the same 4 hours. So they're both going to be putting in 4 hours on this day where they're working together. Now that I have the first 2 columns filled in, I multiply across to fill in the last column for work, right? So we're going to multiply across. Think of this as 4 over 1. So the 4 is going to go on top. The X minus 6 is going to go on the bottom. Same thing here. Think of this as 4 over 1. The 4 goes on top. The X goes on the bottom. So these expressions represent how much work each person is doing. So you've probably wondered this before. Like when you're working with somebody else to get a job done, like for instance, I can think of when I was younger, me and my brother would have to rake leaves. And I would sometimes wonder, like, I feel like I'm working a little bit faster than my brother. I wonder how much of this job I'm actually doing myself and how much he's actually contributing. this is what this is telling me, right? This actually tells me this is the amount of work that John contributes to the job getting done. This is the amount of work that Steve is contributing. He's slower, so he's going to be contributing less work. Together, however, they are getting one job done. So to make an equation out of this information, we're going to take the work that John is doing, which is 4 over x minus 6, add to that the work that Steve is doing, which is 4 over x. Together, their work together is one job getting done. 1 cord of firewood is getting cut and split. All right, so that's my equation. Now I'm out of space, so what I'm going to do is make a little more room down here. So let's kind of skip over the Steve working alone information. We're just going to skip down here, and what we're going to do is find the LCM, right? And first, normally to find the LCM we have to factor, but these can't be factored. They're already too simple. So they are their own factors. X minus 6 is the factor here. X is the factor here. Now notice those are two different factors. So for my LCM, I need both of them in my LCM. So I need an x minus 6, and I also need an x. So this x here doesn't count for this x, right? The factor here is not just x. The factor is x minus 6. The factor here is x. They're different, so they both need to be in my LCM. So we're going to multiply that to both sides of the equation, x times x minus 6. Think of this as over 1. We're going to distribute. So when this gets multiplied to the first fraction, what's going to cancel out is the x minus 6. Again, I'm not going to leave that crossed out because I need a fresh copy to multiply to these other two things. So I'm going to undo that crossing out, but just, again, mentally keep that in mind. The x minus 6 cancels out. So what we're going to have left over is the 4 that was here to begin with times the x that's left over from the LCM. The x minus 6 got canceled out. All right, we'll put a plus sign. A fresh copy of this gets multiplied to the next fraction. This time, it's the x's that cancel out. So what I'm going to have left over is the 4 that was here to begin with times the x minus 6. All right, so I'm going to undo the crossing out here. So I'll have the 4 times the x minus 6 is left over from the second one. And then equals, and even though this is not a fraction, we have to follow the rules for math, which is you have to multiply it to both sides of the equation. So it's going to get multiplied here as well, and I'll get 1 times x minus 6, which is just going to be x times x minus 6. All right, so now we're going to distribute and simplify and see what kind of equation we end up with. I think this time I'm finally going to get my wish, and we will have a quadratic equation. So we're going to distribute the 4, distribute the x. So we'll have 4x plus 4x minus 24 equals x squared minus 6x. So we'll combine like terms. This will be 8x right here, minus 24 equals x squared minus 6x. So this time the x squared is not going anywhere, right? There's not another x squared to cancel out with this one, and so it's going to stay a quadratic equation. Now the reason it's important for us to do at least one example of this type is because solving a quadratic equation is done in a different way. You can't just get x by itself on one side. We have to do something different here. We have to get 0 on one side and then factor the other side. So I like to keep my x squared positive, so I'm going to keep the x squared on the right-hand side, and I'm going to 0 out the left-hand side. So I'm going to subtract the 8x from both sides and add the 24 to both sides so that there's nothing left on the left-hand side. So this is going to be a 0 over here. And on the right-hand side, we're going to get x squared minus 14x plus 24. So it's quadratic. To solve this, we'll factor, right? And so we'll have, we need two numbers that multiply to 24, add to negative 14. That's going to be negative 12 and negative 2, right? And so we're going to get two answers here, which should be a little bit disturbing. I guess I don't need to scroll down. I can just kind of keep working over here. I have plenty of space. That's going to be a little bit disturbing. So we set each factor equal to 0. I guess I already scrolled down, huh? But I don't need to scroll down anymore. So we'll get x minus 12 equals 0 and x minus 2 equals 0. All right. We get two answers. Now, obviously, there can't be two right answers here. All right. So we get x equals 12 and x equals 2. So I have to decide which one of these is the right one. And I'll start with the wrong one to begin with. So if I assume the correct answer is 2, right? So let's say I think this is the right answer. Remember, x is representing Steve's time to get the job done by himself. And in and of itself, 2 hours is a, sensible answer, right, for Steve. But if Steve gets the job done in 2 hours, if we're saying x is equal to 2, then how fast would John get the job done? Sorry, it's a little bit off here. It's 6 hours less than that, so you can't go 6 hours less than 2. We'd get -4 in that case, and that answer doesn't make sense. We can't have John's time be -4 hours. So 2 doesn't work because it makes John's time unreasonable or insensible in this case. All right, so we can rule 2 out as a solution. 2 can't work, and so we'll throw that one out. And so it must just be 12. Steve gets the job done in 12 hours. And so this is Steve's time, right? So Steve gets the job done in 12 hours, which means John gets the job done in 6 hours, right? So Steve, we have to make sure we type the right answer into the right box in Math Excel. So Steve gets the job done in 12 hours working alone. John gets the job done in 6 fewer hours, which would be 6 hours, right? So we minus 6 from that to get John's time. And so that would be my final answer. Okay. Got a couple more word problems, I'm afraid, but this one's not too bad, actually. I'm sorry if it's hard to read. I should have zoomed in a little bit more than I did. I'll read it to you. To determine the number of trout in a lake, a conservationist catches 159 trout, tags them, and throws them back into the lake. Later, 20 trout are caught, 10 of them are tagged. How many trout would the conservationists expect to be in the lake? So I think this is a really interesting problem because I always wondered, first of all, why nature, wildlife rangers or whatnot tag wild animals. Like, what's the point of doing that? And so this gives us a good reason why they'd want to do that. And I also always wondered, like, how do they estimate the population of a certain kind of animal in a certain area? Like, how do they know there's like 5,000 left or whatever? And so this is how they get those estimates, right? So they catch, in this case, they caught 159 fish, and let's see, a conservationist catches 150, tags them. Okay, so we have 159 fish that are caught and tagged. That's important. So they were tagged. Later, they catch 20 fish at random, but only 10 of them have tags. So what we're getting are two different ratios. Let's start with the second ratio here. They caught 20 fish, and out of the 20, 10 of them were tagged. And you could also write it as 10 out of 20 if you feel better about that. But the order, for the first one, the order doesn't really matter. So we have 20 total. Out of the 20, 10 of them are tagged. The first ratio they mention here is that there's 159 trout, 159 fish that are tagged. So you want to make sure you put that number in the same order as these two numbers. The first number here is the total number of fish, right, which was 20 in the second case. And the second number here is the number that are tagged. So this 159 is the number that are tagged, so that actually needs to go on the bottom, not on the top. It's a very common mistake here for students to think, oh, that's a big number, it needs to go on top where this big number is. But this is actually the smaller of the two numbers. The number we're trying to estimate is the total number of fish in the lake, which we don't know, so we're calling that X. But out of that total of X fish, 159 of them are tagged, right? That's how many they tagged and released back into the wild. So that's the order we want to go in. It's total over tagged. Same thing here, total over tagged. And we're presuming that these ratios should be about equal. They might not, again, when you're catching 20 at random, it might not always equal the exact ratio in the lake, but it should be close, right? And so this gives us this equation to solve, which we solve by cross multiplying, right? So we're going to use that shortcut. It's one fraction equals one fraction, so let's take the shortcut here and cross multiply. So we'll take X times 10. That's going to be multiplying these opposite corners together. And then we'll have 159 times 20. All right. And remember what we do when we cross multiply is we set the results equal to each other. So we're going to get X times 10, which is 10X on the left-hand side. And here, I don't know. I guess we should multiply together. What is it going to be? I should have grabbed a calculator when I had a chance. Let's see, 160, that's gonna be 200, and then another 120 on top of that, so it'd be 200, 320. Oh gosh, it'd just be easier if I do this, I think. Trying to do it in my head, but gosh, I'm not that good at it. So we 8, carry the 1, that's gonna be 11, carry the 1 again, we're gonna get 3, and then toss a 0 on the end because of this 0 here, so we get 3,180. All right, and then we're going to divide by 10. And so we're going to get x is equal to 318. So that would be the person's estimate, the conservationist estimate for how many trout are in the lake altogether. All right. So I'm sorry I hope I explained that well. I don't know how good of a job I did, but I'm just going to leave it. One more word problem, and then we'll have a couple other things to do, and we'll be done. The speed of a stream is 2 miles per hour. A boat travels 11 miles upstream in the same time it takes to travel 15 miles downstream. What is the speed of the boat in still water? All right, so this is a distance, rate, time problem. Right? We see all those elements being mentioned here. We have a speed, we have a distance, we talk about the same time here. So this is the formula that we want to use. It applies to two different situations. It applies to moving upstream, and it also applies to moving downstream. So we're going to use a table to organize that information. And I'm sorry, this is, oh gosh, I'm getting really bad at drawing these tables. Oh, I don't know if that's going to work. All right, and we'll make a column for each thing, each variable that's in the formula. So we have R, T, and D, and then we have upstream and then downstream. You might find it helpful here to draw a picture of what's going on. So we have a river, right? So this is my river right here. And the river has a current, right? So the current's moving in this direction, let's say. And we're told the speed of the current is 2 miles per hour. And in this river, we have a boat, right? And the boat's traveling in both directions. I mean, not at the same time, obviously, but in one instance, the boat is traveling upstream against the current. And the boat has its own speed that it's able to travel at, but the current is pushing against that speed at 2 miles per hour. So the boat is working at X miles per hour in this direction, but the current is pushing it 2 miles per hour back. So the net speed there is going to be whatever the boat could do on its own minus the 2 mile per hour current that's pushing against it. So that's for the upstream. That's working against the current. Later, the boat is going with the current. And again, the boat on its own can go X miles per hour, but this time the current is giving it an extra boost of 2 miles per hour. So it's going to go 2 miles per hour faster than what it would on its own because the current is pushing it along. All right, so that would be the speed downstream with the current. The distance the boat travels upstream is 11 miles, so that actually goes here for the distance. And this is where we take a departure from what we're normally used to doing with these tables. We're actually going to fill it in a little bit backwards. We're given the distance, so we're going to plug that in for the distance, 11, and the distance downstream is 15. So we're going to put that here for the distance going downstream. And then we're going to have to reverse engineer this information, and work backwards to figure out what needs to go here for the time. So if I take this formula and I solve it for the time, I divide R on both sides, and I get that the time is the distance divided by the speed. All right, and so we'll do that for each of these rows. To fill in the time, we will take the distance divided by the speed for that row. So for the time for upstream, it's going to be the distance, which is 11, divided by the speed, which is x minus 2. For downstream, we take the distance, which is 15, divided by the speed, which is x plus 2. All right. So this time we have to work backwards. So I don't know, reverse engineer maybe wasn't the right word there. We had to work backwards to fill in the time column using this formula here, distance divided by speed. Now that we have information about the time, we want to make an equation out of this, and what we're told is that these two events happen in the same amount of time. Now when I ask this question in class, I'll say, so if it's the same amount of time, how are these two things related? How do I connect them together? And I'll have students that aren't sure, and I don't know. It's a kind of a mystery to me. Like, if it's the same, what should we do with these two expressions, right? Well, what do we do anytime in math when two things are the same? We set them equal to each other. They're equal. That's what the equal sign is for. The equal sign means these two things are the same, right? And so we're going to set this time, 11 over x minus 2, equal to this time, 15 over x plus 2, because the problem tells me these times should be the same. So I set them equal to each other. And so we get this equation, which we solve by, again, using the shortcut. We'll cross multiply. So we'll get 11 times x plus 2. That's multiplying these opposite sides together. And then 15 times x minus 2 for multiplying these opposite sides together. And then we set those results equal to each other when we cross multiply. So we have this equation to solve. We'll solve it by distributing. So we'll distribute the 11. We get 11x plus 22. Distribute the 15. We get 15x minus 30. And this is a linear equation, so we don't have to get 0 on one side. We don't have to factor. We just have to get x by itself. And I'll do that by subtracting the 11x to the right-hand side. That keeps the x positive, which I think is just an easier thing to do. And while I'm at it, I'll go ahead and add the 30 over to the left-hand side. And that way it keeps all the numbers positive. So what we're going to get here, adding these together, is we'll get 52 equals, combining these together, we get 4x. Right. So these canceled out, these canceled out. This is what results. And I ran out of room here, so I'm just going to move it over here. So now we solve this for x by dividing 4 on both sides. And we get 13. And that's the answer we're looking for. X is the speed of the boat on its own, the speed of the boat in still water, as they're asking here. And so x is 13. That's the answer we're looking for, so 13. I don't know if I quite connected those together the right way. X is the speed of the boat on its own. That's the answer we're looking for. And so when we find x, we find the answer we're looking for, which is 13. All right. All right, so there's one of these problems. This is from 5.7. Solve a formula for a particular variable involving these rational expressions. And most of these have the same quirk that you need to be prepared for. And it's hard to figure out on your own the first time, but once somebody shows you how to do it, it's really not that bad. The first step is to get rid of all these fractions by finding the common denominator, just like we did for the previous equations. So the LCM, we take each factor that occurs, which is basically just going to be each letter that we have here. So we have Q, we have S, and we have F. So that's going to be my common denominator. We'll multiply to both sides of the equation. So I do it in this way. We'll distribute. Again, a fresh copy of this has to get multiplied to each fraction. So think of this as being over 1. When this gets multiplied to the first fraction, the Q's cancel out, and we'll have SF left over. So again, let's just kind of do this mentally. Here, when this gets multiplied to the second fraction, the S's are going to cancel out, and we'll have QF left over. Equals, when this gets multiplied to the right-hand side, the F's cancel out, and we get QS left over. So we made the fractions go away, but the equation becomes a little bit messier than it was before. We're trying to solve it for Q, so we want to get Q by itself. So the first thing you want to do is get all of your terms that have a Q on one side of the equation. Right. And so this one, this term is already by itself over here, QS. So let's bring this term with Q over to the right-hand side so that all of the terms with Q are on one side of the equation. So I'm going to subtract the QF over to the right-hand side. So on the left-hand side, I'll still have the SF. Then I'll have the QS minus the QF. And here's the trick you have to know in order to get to the finish line. And that is, now that you have all your terms with Q on one side of the equation, it's a common factor for these terms, so we can factor it out. So I'm going to factor out a Q from both of these terms, write it one time out in front, and then what's left over is S minus F. This side is still SF, so let me continue over here, if I can write. So we have SF equals Q times S minus F. Okay, there we go. Sorry, I keep pushing the button on the pen. It's hard to hold the pen without pushing the button. I want to get Q by itself. It's being multiplied by SF. So to get Q by itself, we will divide by S minus F. And so what we end up with here is we'll have SF on top divided by S minus F on the bottom equals Q, because these two things are going to cancel out. And so that would be my final answer. That's solve for Q. So again, the trick is get all of your terms with the variable you're trying to solve for to one side of the equation, and all the other terms need to be on the other side, and then factor out the variable that you're looking for. That gets you one of that variable, which you can then get by itself by dividing the parentheses to the other side. So that's how all those tend to work. All right, almost there. I think we have a couple more. Now, I said we just did the last word problem a moment ago. I guess you probably would consider this a word problem, but I don't really think of these as word problems because these are kind of formulaic and they kind of work the same way every time. Whereas for me, word problems are a little bit more dynamic. There's words in both of these, but this one kind of has the same flavor every time. All right, so what's going to happen here, the number of kilograms of water in a human body varies directly. So whenever you see that phrase, varies, either directly or indirectly, those are the two different versions of variation, there's a formula that goes along with that. So if it varies directly, the formula you want to use is y equals k times x. The other type of variation is inversely, and if that's the description they give you, instead of multiplying by x, you divide by x. So you get y equals k over x. So we don't need that for this problem, but just in case when you take the test, it might have inversely here instead of directly. So this would be the formula you'd want to use instead. All right, so it varies directly as the mass of the body. A 93 kilogram person contains 62 kilograms of water. How many kilograms of water are in a 75 kilogram person? So what we might find useful here is instead of using x and y as our variables, we can switch those out for letters that'll help us remember what they're representing a little bit better. So y should represent the number of kilograms of water. So maybe instead of using y, I'll use w for water. And x should represent the mass of the body of the person. So maybe we could use b for body, p for person, m for mass, whatever you might find useful to help you remember what this is representing. So I'm going to use b, see if I can write the b a little bit better here. All right, and so this is my formula. K is the constant of variation, and you should just continue to call that k. Now, in order to answer this question, they want to know how many kilograms of water, I want to know how much water are in a 75 kilogram person, or a 75 kilogram body. So that's going to be b. If I take 75 and plug that in for b, I can't answer the question because I don't know what k is equal to. I don't know how much water there is because I don't know what the constant's equal to. So we have to find this first before we can answer the question. So really these problems have 3 levels to them. Every single time there's 3 levels, or up to 3. It might not go all the way to 3, but it always starts off with first figure out the formula like we just did here. The second step is to find the constant. What is the constant equal to? To find that, they have to give you some numbers to plug in. And thankfully they do here. They tell me a 93 kilogram person, that's the body, right? I should have used P for person, contains 62 kilograms of water, that's W. So I can plug both of these in to my formula, 62 for W and 93 for B, for the body, for the person. And then I can solve this for K to find out what K is equal to. So I'm going to divide by 93 on both sides. And this isn't going to divide very nicely. I probably really do need to get a calculator here. Give me just a second. It may reduce. And that is something that we might want to do. All right. So we have 62 divided by 93. I get a decimal of, it's a recognizable decimal to me. It's 0.66666666, which hopefully you would recognize is one of the more common ones. It's 2/3, right? And so that means this does reduce. So let's see if we can figure out how to get it down to 2/3. It must be 31, right? Because if I divide this by 31, that's how I get down to 2. So I'm going to divide this by 31 and divide this by 31, and this is going to reduce down to 2/3. Right? So instead of leaving it as 62 over 93, let's reduce it down to 2/3. All right. And so K is equal to 2/3. Now, once you know the value for K, you can plug it into your formula because it's not going to change. K is a constant. It stays at that same value for the rest of this problem, right? And so my equation becomes W equals 2/3 times B. And so now I have this equation that is now useful. So now I can take this value for B, which is 75, I can plug it in and get an answer for how much water there would be, right? So W equals 2/3 times B, which is 75. So what's happening there is 75 is getting divided by 3, which gets me 25, and then multiplied by 2, which gives me 50. Right? So when you plug that into your calculator, or when you do that calculation, think of it like this. If you want to do it by hand, you get 50. And so that tells me the amount of water. It'd be 50 kilograms of water. All right, so that's step 3, is answer the question. Step 1, get the formula. Step 2, solve for K. Step 3, plug the number in and answer the question that they're asking you. All right, let's do the same thing here. So the current I in an electrical conductor varies inversely this time, right? So The formula I'm going to use this time is y equals k over x as the resistance, right? So, which they give us some letters to use here. So instead of y, I want to use that. I know that maybe looks like an L, but it's a capital I, right? So instead of y, I'm going to use capital I for current, and instead of x, I'm going to use R for the resistance, right? So use these letters. So this is step one, figuring out what the formula should look like, setting up the formula. Step two is to find K. I can't answer any questions until I know what K is equal to. Thankfully, they give me some numbers here to find K. So the current is 1/4 of an ampere, right? So I'm going to plug in 1/4 for the current, which is I, when the resistance is 2,560 ohms, right? 2,560. So I want to solve this for K, and the way I get K by itself, it's being divided by the 2,560. So to cancel that out, I will multiply by 2,560 on both sides. Right. Or think of it as, well, I guess it's not really a common denominator. I'm just multiplying by this number to cancel it out so that K is by itself. Now over on this side, we're going to get the 2,560 times 1/4, which is simply just dividing by 4. So again, I'm going to use a calculator here. 2,560 divided by 4 gives me 640. Right, and so that's my value for K. Now that I know what K is equal to, I'm going to plug this in to my formula. Right, so now let me say this was step two, right? Step two was plug the numbers in so you can find K. Once you know what K is equal to, I'm sorry, I didn't really use a good color there. It's kind of blending in. Once you find what K is equal to, you plug it in for K, and so I get my equation, I equals, I know K is 640 now, so I'm going to plug in 640 over R. Now we don't leave 2,560 plugged in for R because R is a variable. So the difference there, even though they're both letters, there's a big difference. A constant is a fixed number that doesn't change. A variable is a letter that represents a value that can change and will change. So we don't want to permanently plug in 2,560. We only did this temporarily so we could find K, and then we go back to calling it R because the value is going to vary. It's going to equal something different in just a minute. Now it's going to equal 4,000, right? So I'm going to plug in 4,000 for R. So I get I equals 640 over 4,000, and now we're confronted with the same dilemma we just had a moment ago. We have this kind of not very nice looking fraction that we definitely need to reduce, right? It says type it in as a fraction, but you always need to reduce the fractions. Now the first thing I see we can do here, if they both end in 0, you can cancel out those zeros. It's essentially you're dividing by 10. Whoops, I don't know what I'm writing there. Dividing by 10. All right, so we get 64 over 400 now. All right, so that cuts it down pretty quick. They're both even, so I know they can at least be divided by 2, but I'm betting that something better than 2 is going to work. So I'm going to say, I know at least 4 would work, but even after we divide by 4, I think they'd both still be even. So let's go with 8. Let's divide by 8 on both sides, or not both sides, but the top and the bottom. So the top becomes 8, right? 64 divided by 8 is 8. 400 divided by 8 is going to be, gosh, I should know this. Is it 50? Should be 50, I think, right? Yeah, 50. All right, now they're both still even, so I need to go one more round with this. I think 2, right? So let's divide both the top and bottom by 2, and we're going to end up getting 4 on top, 25 on the bottom, and that's as far as that's going to reduce. So the current would be 4 over 25 amperes, right? And that's what we type into the box right here. Okay, so I think that is the last problem on the practice test. I'm sorry the videos became pretty lengthy, but there was a lot of stuff to explain there. So just make sure you practice it before you go in to take the test. And like I said, be prepared. I try to keep the test to an hour in length. And while I think this one could be done in an hour if you knew exactly what to do and you just went right through it real quickly, it's probably going to take a little bit longer than that. So maybe plan for an hour and a half or so. So good luck with the test, and I'll see you in the next video.